continue our lesson about loose structures. Today we will do some practice. Let's take cyanic acid and draw its loose structure. HCN is a cyanide or cyanic acid. So first of all, what we do, let's remember our previous video. So we discussed we have to determine whether it is a molecular compound or an ionic. So this is molecular, has a molecular structure. Let's write it's a molecule. Okay, then let's find the number of its valence electrons. Hydrogen is in the first group of the periodic table. It has 1 electron. Carbon has 4 electrons. Nitrogen has 5 electrons. So overall there are 10 valence electrons, or we can say 5 pairs. On the third step, if you remember, if not, watch the first video again. So we draw the skeleton. So on the third step we draw skeleton. Let's draw. It can be like this, or maybe like this. We don't know. Let's check. Let's try and see what will be better. So there are 2 possibilities, and of course we cannot put hydrogen in the middle like this, because hydrogen's valence will be always 1, so we don't consider this variant. But let's review the other 2 ones. Let's complete the octet. We know that carbon has valence of 4, right? So let's complete its valency. Let's draw 2 more lines here. In this case, in the second case, okay, we have to draw 4 lines here, because carbon needs to have valence of 4. Let's now have a look at valence electrons. So we see that every bonding is 1 pair. We overall have 5 pairs. Let's see how many pairs we have here. We see that in the first molecule we have just 4 pairs. 1 pair is missing. We can put it like here on nitrogen. And now if we pay attention, we see that around nitrogen we have 4 pairs. Octet rule is considered. If we consider carbon, we have 4 pairs, 8 electrons. Octet rule is followed. In hydrogen we have 2 electrons. For hydrogen and helium we have duplet rule. It's also followed. It's okay. Overall, how many pairs should we have? 5 pairs, so we have 5 pairs. This molecule is okay. Let's review now the other one. Let's have a look. How many overall pairs do we have? 1, 2, 3, 4, 5. Okay, number of pairs is followed. Let's consider the octet rule. Around carbon, octet rule is followed. Nice. Around nitrogen, we have 5 pairs. So 10 electrons. Here we see that octet rule is violated. It cannot be. Moreover, we see that in this case, we get nitrogen with valence 5, and we know that nitrogen cannot have valence 5. So from this, we can conclude that this formula is not correct. This is the only correct one. So let's draw it again. H, C, N, and 1 pair on nitrogen. Good. Let's check their formal charges. Do you remember how we calculate the formal charge? Let's remember together. So formal charge for hydrogen, it is number of valence electrons. Hydrogen has only 1 valence electron, minus number of free electrons, but we see around hydrogen there are no free electrons, no free pairs. So number of free electrons will be 0. and number of bonds. So we see only one bond around hydrogen. It is 0. So formal charge for hydrogen is 0. Let's calculate formal charge for carbon. So number of valence electrons of carbon is 4. We take it from the number of the group where the element is situated. Carbon is situated in the first group of the periodic table. So it has 4 valence electrons. Let's now take minus number of free electrons. We see that around carbon we don't have free electrons. Minus number of bonds. We have 1, 2, 3, and 4. 0. And finally, we calculate formal charge for nitrogen. Number of valence electrons will be 5 minus number of free electrons. We see that there are 2 free electrons, minus 2, minus number of bondings, there are 3 bondings. It's also 0. So as we see, formal charge for all of them are 0. That's good. If formal charges are 0, it means the molecule is stable. Because if there are a lot of formal charge, that molecule will not be stable. If we have a lot of possibilities, in this case, we have to check the formal charge. So the molecule with the least number of formal charges will be the most stable. Okay, let's take this molecule. Let's see what we can do here. In this case, we say it is ionic. Why? Because in the solution it will be divided into ions. There will not be any covalent bond. There will be covalent bonds, but sodium will be separated like this part, and this part will be separated. So there is an ionic bond between these two parts. Right, ionic. Then let's find the number of valence electrons. Carbon has 4 valence electrons. We have 2 carbons in this molecule times 2. Plus hydrogen has one valence electron. We have 3 hydrogens. Plus oxygen has 6 valence electrons multiplied by 2 oxygens, and sodium has 11 electrons. No, sorry. Sodium has 1 valence electron. Let's now find. It's 24 valence electrons, or we can say 12 pairs. The third step, we draw the skeleton. Usually we draw hydrogens around carbons. Yes, it's obvious that it will be like this: CH3, 0C, O, sodium. Yes, sometimes students get confused and they think maybe we can draw like this. Let's draw all the possibilities. So as we see, both of them seem logical. Let's see then. Let's complete the skeleton and then we will understand if it's okay or not. So we know that valence of carbon should be 4. For the first carbon it's okay. For this one it's 3. We should add one more. Here or here. If we add one bonding here, our oxygen will have 3 bondings. Oxygen cannot have valence of 3, so it's not possible. For this reason, it will be here. It will be added to this oxygen. Well, now all the valences are okay. Let's have a look at the octet rule. It has valence 2, but around this oxygen, the valence is full, but around it we see that there are only 4 electrons. So 2 pairs, you see. but according to the octet rules there should be it. So we add 2 lone pairs on this oxygen. Okay, let's have a look at this oxygen. It also has 2 pairs around it, but 2 pairs are missing, so we add 2 more lone pairs on this oxygen. Let's now check. Let's have a look at the overall number of pairs. We see here we obtain that we need 12 pairs. Let's find how many pairs we have in our molecule, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So in this molecule we get overall 12 pairs. And let's move to this molecule and let's try to find what happens here. If we want to draw this like that. So carbon needs to have valency 4. With the first carbon, it's okay, valence is considered. For the second carbon, no, there are only 2. It means we need to make it 4. Okay, 1, 2. If we add here 2 more bondings, carbon gets valency 4. But in this case, this oxygen has problems because it will have now valency 4. But oxygen should be 2. So it's not correct. Okay, what can we do? Let's add these bondings on this side, 1 and 2. Now this carbon has 4, valence 4. But this one, we see that now this has 6, valence 6, and it's not possible. It means that this is wrong. It's not possible. At least it's not stable. But let's return to this molecule now and clarify it better. At the beginning we said it was ionic. Look, ionic. Between this part and this part there will be ions. So we draw it actually in this way. Pay attention what we do. We draw it in a square bracket with a negative charge and sodium with a positive charge. So if our compound is ionic, it can create an ion. It does not have a covalent bonding. We draw it in this way. Let's now have a look in the part which is inside the bracket. About sodium, everything is clear, it's okay. Let's even erase it. Now we are not interested in this part. We drew the new structure. Let's have a look at this molecule. Look at these 2 oxygens. We can draw it also like this, yes? These 2 oxygens can change their position, right? Then this oxygen will remain single. And if we draw it like that without brackets, see, they are called mesomer structures, but that will be another topic in another video. In this case, this minus charge might stay here or it might stay here. So it always jumps. It can be on one oxygen or on the other one. And that's why there is also even the hybrid form how to draw this molecule. C, H, H, H. We draw like this. And we draw the dashed line between them. And this will be the hybrid form of these 2 variants. I will not delve into this topic because I will talk about it in another video. So currently we are interested in putting charges correctly to draw new structures. When the charge is double, it can jump from one oxygen to another one. We draw it out of the brackets. So we put such brackets, as I said, and put this charge where? Not on this, it can always jump. We put it out of the bracket here, minus. This I will have a negative charge. And then, as we said, sodium plus will join here, plus. So stable charge is usually drawn inside of the bracket. Non-stable charge, jumping charge is written out of the brackets. Lewis structure of nitric acid, HNO3. So first, it is molecular. Let's find valence electrons. Hydrogen 1, nitrogen 5, oxygen 6, 3 times, because we have 3 oxygen atoms here. It will be 24 valence electrons, or 12 pairs. And let's draw the skeleton. Valence of oxygen is 2. Then let's add to one of this oxygen, we add double line, but we cannot add double line to both of the oxygens, because in this case nitrogen will have valence 5. It's not possible. So we can add double bond to one of the oxygens. The first oxygen has 2 pairs around it. Octet rule is not followed. We need to add 2 more pairs to follow the octet rule. The second oxygen has only 1 bonding, 1 pair. 3 pairs are missing to complete octet. For nitrogen it's 4. For this oxygen we also need to add 2 pairs to complete the octet. And now let's count the overall number of pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 pairs. Well, I mean that this is a correct structure. I will count only the formal charge for nitrogen and for oxygen. So these are formal charges. But if we now draw its mesomer of this molecule, if we do like that, of course in this case nitrogen will have 1 plus 1, and this oxygen will have charge -1. As we see, this +1 is a stable charge, but -1 is jumping. It's stable and it's jumping. So stable charge is written inside the brackets. Let's draw the hybrid form. Stable charge is always on nitrogen. We draw it like plus or +1. About oxygens, we see that it's always jumping. So this jumping charge will be written out of the brackets minus. So this is all for today. You can take more molecules, practice yourself. See you in our next videos. Bye.